Okay, good morning. Can you hear me okay? Yes, great. So thank you for being here this morning. My name is Christine George. I'm the CEO of ERGOSUP, and I have been the CEO since October of 2021. So our mission at ERGOSUP is to provide on-demand, decentralized, high-pressure hydrogen solutions. And we will get more into that, but I want to mention that our technology has a couple of unique features. The first one is that we can produce hydrogen at high pressure without any mechanical compression. And the second part is it's a batch process, and between the two steps, we are able to store hydrogen in the form of protons. So it's ionic storage, but we'll come back to that. So first, I'd like to present the team here. We are a team of about a little bit over 20 people, 13 engineers, a multidisciplinary team, since we have electrochemistry as well as thermic, mechanics, and fluidics. We're dealing in acidic environments as well. Also want to mention that we have our technology is patented. We have filed about 11 international patents internationally. And also the technology has been awarded through the 2030 Innovation Challenge, as well as at the 2019 Las Vegas Forum. Also, I want to mention that amongst our investors, we have a few prestigious companies and funds, including Air Liquide, AP Venture, Demeter, BPI France, and Kouros. So our high-pressure solutions, well, we are targeting those target markets here. So the last mile delivery, drones, and community refueling. So generally speaking, light mobility applications. Last mile delivery, as you know, our behaviors, consumers' behaviors have changed quite a bit with e-commerce, and I think COVID probably accelerated the process. So expectations are different. Also, the evolution of regulation in urban cities is evolving with low emission zones, making the traditional means of delivery a little bit more challenging. And so that's where cargo deliveries, or what we call cyclo-logistics, is really exploding right now. And so bringing the ability to meet the demand, but also to reduce noise, reduce carbon footprint, and congestion in urban cities. Hydrogen has a role to play in this market, providing more autonomy and the ability to carry heavier loads as well. In the other market for the drones, here we are seeing more and more applications that would have traditionally been managed by helicopters or thermic drones being replaced by electric assisted drones. And they allow to be, of course, reducing the carbon footprint, but also less noisy. And again, here, hydrogen is particularly pertinent for applications with longer autonomy, such as surveillance or utility corridor patrolling. And so that's the end game here. And lastly, we target the community refueling, and specifically for distributed stations of smaller sizes to network the territory. And we have a partnership with Attaway on this particular market. So to talk a little bit about the split electrolysis, our technology, on the left-hand side, you have a schematic of the traditional electrolysis, where so you supply current to the electrodes and producing hydrogen and oxygen at the same time. Because of that, there needs to be a membrane to separate the two so that they don't permeate with each other for safety reasons, obviously. And co-producing both at the same time, also at a limited pressure due to the presence of the membrane to avoid permeation between the two. On the right-hand side is our patented technology that takes place in two steps in the same reactor with no membrane. So first step, we apply power. At that time, we release the oxygen But instead of releasing hydrogen, there is a zinc salt in the electrolyte that actually is being is fixated on the cathode instead of hydrogen being reduced. So as a consequence of that, the hydrogen is being captured in the electrolyte in the form of H plus protons. That's what we call the ionic storage, and we'll come back to that. Then we can actually interrupt between step 1 and 2, and that's where the storage capability comes in. In the second step, which is a spontaneous reaction, so there is no need to supply energy, neither thermic nor electrical. The zinc salt is being dissolved back into the electrolyte, and hydrogen is then being reduced at the cathode. The reaction is spontaneous, and the kinetics is such that the pressure is going up in the vessel all the way to the working pressure, and then being released into a relatively small purification system, because since we are dealing with high pressure already, the gas is pretty pure. Sorry. Oh, it still works. So to recap on the competitive benefits of our high-pressure solutions, so it's a simplified system. There is no mechanical compression. We can produce directly all the way to 300, 350 bars. Also, there is no membrane, as we spoke about. So that obviously has an impact on being able to reduce both CapEx and OpEx in terms of maintenance. And the fact that the gases are not produced simultaneously brings an intrinsic higher purity of the hydrogen in the second phase, which also reduces significantly the potential of having oxygen and hydrogen mixed from a safety standpoint. Also, our technology is on demand. It's for decentralized supply and also fully integrated. The supply mode, the conditioning can be customized to the customer need. So that can be into a high pressure storage that can go directly into a network or a dispenser or plug and play bottles that can be used, for example, for drone applications. Our capacity is in the range of 0.5 to 5 kilograms at 350 or more bars. So let's talk a little bit about what we actually did, high-pressure solution developments. So we started on the left-hand side with a rather small system of 100 gram at 100 bar. And really the purpose here was to demonstrate the technology on a full-fledged product. We have a couple of those units at customer sites. One of them is actually installed in Marseille and cycling automatically and being remotely monitored from our office in Montélimar. Then we developed a functional prototype that was through a partnership with a dronist, Delair, and also is a project through the DGA. And on this one here, the application was for drones. You can see the little bottles, the plug-and-play bottles, which were used to feed the drone. We are working right now on a pre-commercial product for this one, which will be around 1 kilogram per day at 350 plus bars. And that's coming next year. Right now, we are in the process of starting up a new unit, a new prototype. That's a step up in size in terms of volume, so 2 kilograms per day at 150 bar, and that's a stepping stone for us because it's going to be a new concept that will be used for a modular approach in the future. And then going forward, we are working on a product line between 1 and 5 kilogram at 350 bar or more that will be containerized and transportable. So we spoke about the high pressure side of things and not so much about the storage. So let me come back to that other set of unique benefits from the technology. So as I explained in the first step of the process, we produce oxygen. Then when oxygen is released, hydrogen is captured in the electrolyte. And then in a second step, hydrogen can be reduced. But we can stop between those two steps. And that's where the ionic storage comes in. So it's intrinsically safe in the sense that there is no high pressure, there is no cryogenic temperatures, and it can also be contained for as long as we want. So it can really act as long-term storage. The other part is the Seveso regulation is much less constraining for sulfuric acid, which is the acid that we use for the electrolyte. Essentially below 50 tons, there is not even a need for declaration. There is a declaration between 50 and 250 tons. And above 250 tons is where there is an authorization. So a very broad scope in terms of ability to store on site. Also mentioned that the hydrogen is released without the supply of energy, whether it's thermic or electrical, which from a backup standpoint makes it obviously an intrinsic benefit in terms of reliability. When you need the hydrogen, you don't need to have any utilities, essentially. Let's talk least but not last about the cost. Essentially, our medium to store the hydrogen in our technology is through the zinc deposit and in the acid, in the sulfuric acid. And when you look at those two components, it actually amounts to about half the cost of what would be a traditional high-pressure storage, which would be in the range of 350 to 300 euro per kilogram. With our technology, would be about half of that. I wanted to highlight the fact that a lot of the time when we talk about LCOH for hydrogen, we really talk only about the production part of it. However, as we know, there is more and more renewable energy being integrated in the system. We also, so as a consequence of that, there is more price volatility on the grid. There is also price volatility due to other geopolitical events, as we well know right now. But the point being that in order to have an optimized LCOH, loaded cost of hydrogen, you need to run flat and ideally at a low cost. So when volatility comes in, it's difficult unless you have storage and affordable storage to actually optimize that cost. And so really the LCOH should take into account the storage. And that's where we believe that with our technology that integrates both the production and the flexibility to be a storage, to act as a storage, that it has a unique position to fill. And so we are still in the early stage of development on this storage axis here. And we are targeting between 100 and 1,000 plus kilogram per day in terms of capacity. And we would certainly be very happy to speak to you if there is interest in being a part of this development, if you have needs around storage, as we just discussed. So to wrap up, I'd like to invite you to visit us on booth F08. And we would love to talk about either our high-pressure solutions or our storage developments. Thank you. Any questions?
Hello. Hi. Thank you for your presentation. I have two questions, please. The first one about the efficiency of the electrolyzer. What's the efficiency? And the second one is for conventional electrolyzers, we need about 50 kilowatt hour to produce 1 kilogram. How much energy, electric energy, we need to produce 1 kilogram?
So what I'm going to say is that because our process by design, the fact of depositing the zinc as an intermediate step has an impact of about 20 kilowatt hour additional per kilogram on the efficiency. However, there is no need for compression, so you need to really look at the whole cycle and look at the full supply chain. Any other questions? No? Well, thank you very much, and hope you enjoy the show. And please come visit us. Thank you.